Okay, I see you have survived the part 1 video. That was pretty rough, going through the proof of the fundamental theorem of calculus. So I award you a big prize and a pat on the back if you made it this far. But now we get into really what we want to be able to do, and that is apply it. And so that's not going to be as difficult as the proof was. So here again is the fundamental theorem of calculus, right? Little f is continuous on the interval from a to b. The definite integral from a to b of that function is equal to capital F of b, right, minus capital F of a, where capital F is the antiderivative of f. So we need to find the antiderivative. Notice if we can't find the antiderivative, we're going to be in trouble. We're not going to be able to use this theorem, right? We've got to be able to find the antiderivative. It's got to be something that's relatively easy to find. And then all we have to do is evaluate it at the upper limit and then at the lower limit and subtract in that order. So make sure you remember how we're subtracting there. And it kind of should make sense that it would be b minus a. If you think about delta x, right, being b minus a, the length of the interval going from a to b is b minus a. It's got the same idea in this sense, right? I don't know if that helps you remember the order, because that is important. If you subtract, obviously, in the opposite order, you're going to get -1 times the actual value of the definite integral. Okay, so let's take a look at this notation, and I'll use this little vertical bar notation, as I said. The value of the antiderivative evaluated at b and evaluated at a. So this is the notation that means this over here on the right. Okay. So my first example, 4x plus 3, very simple one. What's the antiderivative of 4x plus 3? So now it's like we were doing a little while ago. What's the indefinite integral? If I just said what's the indefinite integral, you hopefully will say 2x squared plus 3x. I hope that's easy at this point. All right. So it's 4. The antiderivative of x is x squared over 2. 4 times a half is 2. And then the antiderivative of 3 is 3x. That's the antiderivative. Some of you are saying, wait a minute, there's something really important you forgot. A plus c. I always remember you have to put a plus c for the antiderivative. And you're right, we could do a plus c. But here's the thing. If I put a plus c for capital F, and I evaluate it at b, I'm going to have a plus c there, and at a I'm going to have a plus c, and I'll have a c minus c. What's c minus c? 0. That constant will always go away. So you can choose any constant you want, might as well just choose 0. And so that's what we're going to do. We're not going to have the constant of integration when we're doing this, and we're going to evaluate. So this is the capital F of x here, right? And again, we're going to do this notation. So this is the notation we use, antiderivative, right, evaluated at the upper and lower limit. And so this means plug in 3, right, plug in 2, or sorry, -2, and subtract, right? It's got to be in that order. Okay. So, well, plug in. Well, I didn't plug in here, did I? Plug in 3. Let's try that again. Plug in 3. Okay. Sorry. So here I get 3 squared is 9 times 2 is 18. 18 plus 9 is 27. Here I get 4 times 2 is 8. This is -6. 8 and -6 is 2. 27 minus 2 is 25. And we're done. Think about how we were doing this before, right? We were doing a approximating, doing a right-hand sum, perhaps, right? And then we're getting that sum, and we were pushing n to infinity, and finally getting this value. Now we get it very quickly. Very quickly. Let's look at another example. For this one, my first step before I proceed would be to rewrite this integrand, the function we're integrating here. This is fine, but I'm going to rewrite this as -5 what? T to what power? What power should that be? -2, right? I want to do that so that I can make use of the power rule for finding the antiderivative. Okay, so what is the antiderivative? What's the antiderivative of 3t squared? T cubed. Be careful, I see a lot of people get confused and they'll say, they'll write 6t, because what they did is they took the derivative, brought the 2 down, and they found the derivative. We're not finding the derivative, we're finding the antiderivative. So if anything, once you have your antiderivative, take the derivative of that and make sure it's what you started with, as a quick check. Here, the 5 is a constant multiple, so minus the 5. And then what's the antiderivative there? Remember, it's the power rule. Add 1 to negative 1. Add 1 to negative 2, which gives me negative 1, and divide that by negative 1. So there's the antiderivative. Okay. And we're evaluating this at 1 and 2. Let's go ahead and just rewrite this out. Whoops. I like to go ahead and rewrite it out because I've got t cubed, of course, minus a negative. What's that going to happen? Plus, right? And then 5t to the negative 1 power, I'm going to write as 5 over t. Right? That's 5 times t to the negative 1 power. That just helps clean it up for evaluating purposes. Okay? And so we plug in t is 2. T is our independent variable here. T is 2 cubed plus 5 divided by 2 minus 1 cubed plus 5 divided by 1. Right, so I evaluated 2, evaluated 1, and subtract in that order. So this gives me 8 plus 5 halves. 8 is 16 halves, right? 8 is 16 halves plus 5 halves. That's 21 halves. 1 cubed is 1 plus 5 divided by 5, so that's 6 there. Oh, I changed my minus sign to a plus. That's real interesting. I don't know what's going on there. That's a minus sign. Okay, so 21 halves minus 12 halves. 21 minus 12 is 9. So 9 halves or 4.5. That is your value of your definite integral. Value of your definite integral. Isn't this fun? Lot happier. Now this one, you would have real trouble trying to do the Riemann sum and then take the limit as n goes to infinity because of this 5 divided by t squared. We can do polynomial functions like 3t squared, but this, that's not going to be doable even. And so this is a very powerful thing that we have here. We have really opened up a whole bunch of functions we can evaluate the definite integral of. And here's one in particular, the sine function, just the basic sine function. Up to this point, we would have real trouble trying to evaluate this. We can approximate it. We can use, right-hand sums with, left-hand sums with n equal, a finite number, 10, 20, or 30 subintervals, and get pretty good approximation. But now we are going to do this very quickly. I just want you to note in this problem, this is the graph of the sine function here. From 0 to pi, the sine function, right here, 0, pi is right there. 3.14 right there, pi, right? The sine function is positive on that interval. So the value of this definite integral actually represents the area under the curve of the sine function from 0 to pi. And so what do you think that is? What do you think the area under the curve of the sine function is from 0 to pi? Take a guess. You could sort of see that it's, a little more than 3 wide, but you're missing this part of the area. So what do you think? Okay, we're going to find out real easy by the fundamental theorem of calculus. What is the antiderivative of the sine function? So you've got to be careful here. What's not the derivative, but the antiderivative. The antiderivative is negative cosine theta, and that's the tricky thing, right? The derivative of sine is cosine, positive cosine theta. The antiderivative of sine theta is negative cosine theta. We're evaluating this at pi, the upper limit, so it's negative cosine of pi minus a negative cosine of 0. Okay. Well, cosine of pi is how much? That is negative 1. And you're going to have to give me the exact value for sine, cosine, tangent, and so on. You can have a unit circle if you need to. That should be, a lot of you should be pretty obvious how to do this right. And so we know at pi, the ordered pairs here represent what? Cosine of pi, and y is sine of pi. So cosine of pi is negative 1. Right? That goes with the x coordinates on the unit circle. Right? So we go around the unit circle. So like cosine of pi over 6 is square root of 3 over 2. So you should be able to get the exact value. That's what I want. I want a calculator approximation for square root of 3 over 2, say. Okay. In this case, it's negative 1. And then cosine of 0 is 0. Sorry, cosine of 0 is 1. I don't know what I'm saying anymore. Cosine of 0 is not 0. Cosine of 0 is 1. We're over here, right? Sorry. Okay. Have a momentary lapse of reasoning there. Okay. But it's a negative 1, right? So what happens here? I get a bunch of negatives. Minus negative 1 is 1. Minus negative 1 is 1. I really have what? 1 plus 1, which is 2. Was that your guess? That shaded area was exactly equal to 2? That's pretty incredible. That is pretty incredible. Don't kind of expect it to be that nice of a number, but there it is. Okay. Let's look at a couple more examples here. Let's throw the exponential function, e to the x, into the mix. In this case, going from negative 1 to 1, so negative 1 is here to 1, this is the e to the x function. It's positive on that integral, so I'm going to get this shaded in area. Okay, what do you think that shaded in area is? Is it like 2 again? Is it a nice number? Well, let's see. It's actually an easy problem to do now that we have the fundamental theorem of calculus. What is the antiderivative of e to the x? That's easy. It's e to the x, right? And we evaluate it at 1, so that's e to the first power minus e to the negative 1 power, and so we get e minus 1 over e. Okay. So it's not a nice number like 2 or 3 or 1 or something, but it involves the base e. Now, keep in mind, if you're checking answers like in the back of the book or simplifying, you might see something like this, e squared minus 1 over e. I hope you understand how these two things are equal. Basically all we did is combine by finding the common denominator of e and then subtracting the numerator. So keep in mind, you get this answer, you check in the back of the book, or you check something, you see this, you got to realize it's the same thing. So you do have to give exact answers. You want to use your calculator to approximate this now? I mean, you can. That's fine. You can do that. Okay. In fact, let me show you real quick in the TI 83 that under math, if you go to the bottom, I'm going to jump all the way to the bottom, you will see something called FNINT, function integrator. Now, this is an old model TI calculator, so it is not going to do what a lot of you probably have. When you hit enter, you'll actually see an integral sign with a space for the lower limit, the upper limit, the function, and then D space, and of course the space is the variable you're using. So if you use X in your variable for your function, and you can actually type all those things in and it will approximate the integral for you. It's not going to give you this answer, but it will approximate it. Okay. If you have the older model like I do, there's a syntax to this, and the syntax is you put in the function, which is e to the x, okay, comma's right above the 7 key there, if you don't know, right above the you put comma, you put the variable that you're using, which is x, comma, the lower limit, which is -1, make sure you do the little negative sign down there at the bottom, and then +1, upper limit. So it has to be in that order, the function, the variable, right, and then the lower and upper limit. So, but if you have the newer models, it will look just like this, and you'll put these values, all these values, in their appropriate spaces. Okay, and hit enter, and there's the approximation. Just as a check, is that what we have here? If I look at the quantity e squared minus 1 and divide all of that by e, okay, so there's what we have. Is that the same thing? Yeah, it is. And so you can see, you can do some approximating and checking at least with this function integrator. Okay, so it's not It's just an approximation, but obviously it's doing a really good job of that. But again, when I ask for you to give me the answer to number 4, I'm not looking for this answer. I'm looking for this, right, or this, the exact value. This is exact. This is a calculator approximation. You give the calculator approximation, but you have to give the exact value, and you have to show supporting work, which is not much. Okay, let's do a couple more here. What about the integral of 1 over u, the independent variable is u here, from 1 to 5? What's the definite integral from 1 to 5 of 1 over u du? Well, fundamental theorem of calculus says, what's the antiderivative of 1 over u? Natural log of absolute value of u, right? That's the antiderivative. You remember that? Right? From 5 to 1. Of course, the absolute value of 5 is 5, so this is the natural log of 5 minus the natural log of 1. Natural log of 1 is 0, and so our answer is the natural log of 5. That's the exact value, natural log of 5. Now you can approximate like we did above, but that's the exact value. And that's a powerful thing. Again, being able to do this would have been very challenging up to this point. Now fundamental theorem of calculus is a piece of cake. All right, last one, and then we'll stop this portion of the lecture and we'll do some more in the next video. But what about this one here? That's pretty complicated. What's the antiderivative of this? Do I just take the antiderivative of the top, antiderivative of the bottom, and divide? No, because we know, thinking back, taking the derivative of a quotient, it's not that easy, right? There's a big, ugly quotient rule. You can't just take the antiderivative of the top and antiderivative of the bottom and good to go. No. So what do we do here? Well, the thing is, you want to simplify. You want to simplify this integram. Okay. So how do you simplify that? Well, let's look at this. It's x squared minus 1 over the square root of x. That's x to the 1/2 power. Let me do that first of all. Okay. I can break this up, right, into the difference of two fractions. Do you see what I've done here? Right? Or basically what I'm doing is distributing, right, dividing both of these terms in the numerator by the denominator. And then I'm going to simplify each term by what? Dividing, I subtract the exponents, I get x to the 2 minus 1/2 is 3/2 power. And then this is 1 over x to the positive 1/2 is what? X to the what? Negative 1/2 power. And so this becomes the integral from 1 to 4 of x to the 3/2 power minus x to the negative 1/2 power. All right. So that's the trick, is to rewrite it. Now we can find the antiderivative. What's the antiderivative of x to the 3/2? So remember, I add 1 to the power, antiderivative's power rule, add 1 to 3/2, that gives me 5/2, right? And then I'm going to divide by 5/2, right? But what is the same thing as dividing by 5/2? Multiplying by what? The reciprocal 2/5. So just look, if I take the derivative of this, bring the 5/2 down, that becomes 1, subtract 1, I get x to the 3/2. Minus what? Well, I'm going to do the same thing. Add 1 to negative 1/2, I get what? Add 1 to negative 1/2 gives me positive 1/2. Divide by 1/2 is the same as multiplying by what? 2. There's the antiderivative. Check. Take the derivative of this and make sure you get back to this. Always do that, right? And I'm going to evaluate this now at the upper limit, lower limit, and take the difference. So I've got 2/5, 4 to the 5/2 power, minus 2. Now I'm going to go back, square root, right? So x to the 1/2 is just square root. I'm going to just go back to the square root, right? You know that. And then at 1, okay, and 1's pretty easy. If I plug in 1, I know what's going to happen. I'll just go ahead and do this 1 to the 5/2 power minus 2 square root of 1, right? But of course, this is 1 and this is 1, so that's going to be easy. I'm just going to have 2/5 minus 2 here. 2/5 minus 2. What is 4 to the 5/2 power? Well, 5/2 means square root and then to the 5th power. So this is the square root of 4 and then to the 5th power. Square root of 4 is 2. 2 to the 5th is 32. 32 times 2, 64 fifths. So there's this expression. Minus 2 times what? Square root of 4 is 2. 2 times 2 is 4. And as we said here, we had 2 fifths minus 2. Right? So we have a little bit of work to do. I'm going to go ahead and let you complete that out. Well, actually, let's see. 64 fifths minus 4 should give you 44 fifths. So it's 64 minus 20 fifths, right? 64 fifths minus 20 fifths. 4 is 20 fifths. And then 2 fifths minus what? 10 fifths. 2 minus 10 is negative 8 fifths. And notice it's minus and negative, so it becomes plus. 44 plus 8, 52 fifths. 52, write a 2 down there. 52 fifths is the exact value. Or, you know, as a decimal in this case, you can write 10.4. That's what that is. But that's the exact value. Okay. So this one a little more involved, and that's the key. If you can't immediately find the antiderivative, don't try and force things. See if you can simplify algebraically and make it easier to do. Okay, that's going to be an important skill. Okay, we'll stop here and we'll do some more in the next video.